Okay, so let us now go to a normalized, what is this? Normalized Laplacian of the Gaussian. Okay, so that is normalized log. Okay, now I'll just take so what we do is we'll actually analyze it by taking a step signal. Okay, let us say that right, this is the I don't know what I did. So let us say that this is how it is, and this is my intensity, okay, I of x versus x in 1D, and here it is 0 and whatever, right, and then here it becomes 1, and this is some x naught, okay, where there is actually a transition, right, from 0 to 1, right. So now we are we will first see how it actually reacts to an edge. So our I of x, right, in terms of a unit step will now be what? U of x minus x naught, right, that you all know. U of x minus x naught, right, is what your I of x is. Now let us convolve it with a log filter. What does that mean? That means that let me take I of x, let me convolve with, let me call, if I call this one a Gaussian, let us say I call this as g sigma of x, which is 1 by root 2 pi sigma e raised to power minus x square by 2 sigma square, and this is my g sigma. Then a log will be like d square g sigma of x by dx square, right. This is what I want, a double derivative of the Gaussian, right, where g sigma is that. Okay. So this is nothing but u of x minus x naught convolved with d square g sigma of x by dx square. Okay. Then you can play the trick that this is the same as d by dx of u of x minus x naught convolved with d sigma x by dx. This is okay, right. Now what is this? Delta of x minus x naught convolved with d of g sigma x by dx. And we know that if you actually convolve something with actually a delta, you get back the same signal. In this case, it shifted, right. So what should we get as output? d g sigma x minus x naught dx, right. That is what we will get. Now, what is so what is our so okay, let's first find out what is our d g sigma x by dx. Okay, what is the next one? So you have your gx of sigma, g sigma of x. You have your g sigma of x as 1 by root 2 pi sigma e raised to power minus x square by 2 sigma square. Let us do d sigma, we need with respect to dx. There is also another sort of a derivation that is more interesting that you will see later when you actually differentiate with respect to sigma. Okay, but in this case this is all with respect to x. So you get 1 by root 2 pi sigma, then with respect to x, right, so you have like e raised to power minus x square by 2 sigma square, and then what will you get? Minus 2x into 1 by 2 sigma square. So then you have this 2 and 2 will cancel, and you will get minus what is it, 1 by root 2 pi sigma cube into x into e raised to power minus x square by 2 sigma square. So if you go, so therefore, right, what we need is d g sigma of x minus x naught It is what we got in the earlier one, right? This is what we got, right? This is a response, right? This is the response of log to a step edge, and that is the thing on the left. So then this becomes minus 1 by root 2 pi sigma cube. In the limit of Gaussian, sigma tending to 0 becomes what? What does it become? Impulse, yeah, right, that you all know, right? E raised to power minus x naught the whole square by 2 sigma square, right? That is what we are. D sigma will look like minus 1 by root 2 pi sigma cube x minus x naught, yeah, e raised to. Okay, so let's call this as equation 1. So one of the things, right, that we should be able to see is that so as an aside, right, we can actually ascertain one thing. What is that? This is what is the response, right, to the edge as a function of x. And what is the first thing that actually emerges out of this equation? That yeah, right, that has a 0 response at x equal to x naught, which is what we expect, right? That is where the 0 crossing is actually, right? So right aside, clearly the response is 0 at x equal to x naught, which is where the edge is. So we know that a log will give a 0 crossing where the edge is, right? So where the edge is. Okay, this is okay. This is something that we knew all along, but earlier we never showed it formally. We knew that plotted, that's what happens, and okay, this also emerges. Tell me something, right? So what will be the area under the log function? This Mexican hat, right, that you have, no? We saw that, right? Where is that? Oh no. Where is that Mexican hat? I thought I showed it somewhere. Oh, I think here. See this guy, huh? Yeah, right. So what do you think? What do you think is the area under this signal? Is it 0 or it has to be 0 or what is it? Why are you doubtful? I mean, I think we said something about this one Mexican hat, right? What kind of a filter did we say it is? A band pass filter. Can a band pass filter have a non-zero strength at omega equal to 0? Can't, no? It should be 0, right? Then only it's a band pass filter. If it allows 0 frequency, how can it be a band pass filter? Then what was the frequency response of this guy? Minus omega square plus nu square into e raised to power. That's what we saw, no? When we did the frequency response. Put omega equal to 0, nu equal to 0, it has to be 0, right? So in fact, it's actually a wavelet, right? I do not know how many of you have done wavelets, and also, right? So it's actually it's you can change the scale and all, and then then it becomes actually a wavelet. So it has various So this log is actually a very kind of interesting kind of a beast. Okay, so clearly the response is 0, and then okay, now right, this is okay. Now what we want to know is the peak. Okay, the peak can be found as follows by equating d by dx of u of x minus x naught convolved with d square g sigma of x by dx square equals to 0. So, we want to find out where exactly, right, does a maximum occur, okay, which then means that I mean if you had a function whose maxima or minima you wanted to find out, you will take a derivative equated to 0 to find out what exit happens, right. Now, we have, so we know that, right, all of this is equivalent to this, right, and therefore, if you do kind of d by dx of equation 1, which is actually d by dx of equation 1, So, if we do that, right, then what will happen? So, we can pull out minus of 1 by root 2 pi sigma cube, and then maybe I should do x minus x naught, and then we are doing d by dx, right. So, e raised to minus x naught the whole square by 2 sigma square into minus 2 x minus x naught by 2 sigma square plus e raised to power minus x naught the whole square by 2 sigma square. Okay, so we can actually pull out this minus 1 by root 2 pi is common anyway, sigma cube, and then this 2 and 2 will cancel off, and then we can pull out e raised to power minus x naught the whole square by 2 sigma square, and then we can say 1, okay, for this minus, okay, there is a minus sign here, right, minus x naught by sigma square, right, not I mean 2, just by sigma square, yeah, this is what it will be, and this we want to equate to 0, right, in order to get the x at which there is a peak, or there are probably multiple peaks, we do not know, but because it is square, right, so expect multiple peaks. So, okay, so then this means that 1 minus x naught whole square by, yeah, okay, yeah, so I think this is okay. So, 1 minus, so that means that x minus x naught the whole square, it is equal to sigma square, right, from there. So, if you just send it to the other side, or we can say x minus x naught is equal to plus or minus sigma, or we can say x equal to x naught plus minus sigma. Okay, so the peaks occur at sigma to the left and sigma to the right. I mean, which is what I think in our figures and all, right, we keep showing, right, when we see that it's a response, right. So, it's like sigma. I mean, if you have a stage, I mean, are you able to see this cursor? Huh? So, it's like here and here, and there is one on the left and then there is one on the right, and it's like sigma apart. Okay. Now, right, this is where these peaks occur. Where these peaks occur. But then what exactly is the peak value, right? That if you want to find out, then we should go back to that d sigma. Okay, so what is the peak value then, or what are the peak values, right? If you want to know what is the peak value, then we should go back to this. Where is that? So equation 1, right? So which was what is it? So which is that 1 also u x minus x naught convolved with d square g sigma x by d dx, which turned out to be minus 1 by root 2 pi. What did we have? Sigma cube. Okay, now in this equation, right? So in this equation, right? So yeah, so we need to go back to this equation 1, and then there, right, we have to substitute for x, correct? X at those extrema. So what do you get then? X is x naught plus minus sigma, right, and then you have a minus x naught, by the way. So it's x minus x naught, right? So that is, so this is your x, e raised to power, again you have x in its place. Let's put x naught plus minus sigma minus x naught the whole square by 2 sigma square. Okay, and therefore the peaks, right, if you see, so I get, so if I put x equal to x naught plus sigma then I get the peak value to be, then the peak value is minus 1 by root 2 pi sigma cube. So x naught will cancel off, and then I will get sigma. What happens here? E raised to power minus, so you get 1 by 2, right? Sigma square will cancel off, so you will get like minus 1 by 2. Okay, and if x is x naught minus sigma, then the peak value is minus 1 by root 2 pi sigma cube, and then you get minus sigma here. This of course remains minus 1 by 2, which then means that so the peak occurs at, so the peaks occur at, no, not occur at, I mean, so the peak values are rather, so the peak values are not where they occur, of course, where we know the peak values are. Okay, now this sigma will, one sigma will cancel out, right? So we will have like minus 1 by root 2 pi sigma square. So we can write kind of, okay, so can we write plus minus e raised to power minus half, right? Okay, now if you see, right, what do you need? I mean, see, now you can clearly see why the strength was falling off, right? I mean, that curve that I showed, no, as you kept increasing your sigma, this sigma is actually playing kind of a spoil sport now, right? So it's suppressing the strength, and therefore if you wanted something which should ideally be invariant to sigma, what would you now do? You would simply multiply this response by sigma square, right? If you do that, then this becomes, and the peak just stays at minus 1 by root plus minus 1 by root 2 pi e raised to power minus half, which is just a constant, right? And that will not interfere with our analysis then. Okay, that is what is actually a normalized Laplacian. So always, right, they will write sigma square, okay, this one delta square f, but we should remember why that sigma square came, right? The sigma square has come precisely for this reason. Okay, so in order to okay, so which means that, so the strength falls with increasing sigma, so to make the strength invariant, to sigma, or you don't want it to sigma, multiply log by sigma square, and this is all for a step edge, by the way. Okay, I mean, right, this is a response and all that we use a normalized log, right, that we kind of typically use. This is all coming from analyzing a step edge. So multiply log by actually sigma square to get normalized log. Okay. Now if you see, right, if you see, what will happen is that when you have, I don't know whether I have a slide for that. So now when you have a blob, let's see if I have a, so now if I no, not this. See now. See, for example, an unnormalized guy would have kind of say died off like that. Whereas when you have a normalized, scale normalized, right, or when I say normalized, I mean scale normalized. So then you see that these peaks, right, they don't fall off, right. Then what happens is you keep on increasing, right. There comes a point when it actually hits an extremum, and then again, right, again. So the point is, right, this has to do with the way, right, with the way, okay, what do you call, with the way this response behaves, and you get a point, right, where the maximum occurs, and then after that, right, again it kind of begins to fall off. What do you think might be the reason why? Let's say, of course, it's clear from the math that there was a point, right, where of course it had a peak, which means that, right, elsewhere of course it didn't have a peak. But is there some intuition into why this might be going on? No, I'm saying no. Okay, one thing is that we just accept the fact that, well, we had an extremum, and therefore right, at that point, right, we get a peak, and then elsewhere we don't have a peak. That's the kind of simplest way to simply say, right, go with what we had, right, as the kind of, right, as the math. But then, right, I'm just asking if Is there some other way to kind of interpret why the strength is decreasing beyond a point? Or, for example, why, let's say, right, if you had a blob, then right at some scale, right, it actually snugly fits in, and then at other scales, right, it sort of begins to drift away from the maximum. This should have something to do with the area, right? See, I mean, a response is after all what? I mean, it's simply a sort of a dot product, right? It's like an inner product, right? Between two functions. So if you think about it, right? If I were to think about it, right? So if I have okay, no, this is, let's go back to, so for example, okay, so let's call the scale normalized, okay, that's the actual name. Let's also use the same name, scale normalized log. So what I'm saying is, right, see, if you had a step like this, right, let's say it's 1 here, it's 0 here, then again goes back to 1. Okay, now I have, let me draw, right, 3 kinds of Mexican hats. Okay, one, I mean, I'm not drawing it exactly, but you know, one like this, okay, another, okay, or for example, okay, or for example, right, a simpler thing to sort of do it is that, say, is that I have a Mexican hat at a certain scale, then I'm examining this, then let's say I'm examining another like this, and I'm examining another like this. So in each case, the blob width is changing, right? So, right, it's like saying that I mean, you know, I have a blob of kind of say radius r, and this r, right, in some cases it's very big, in some cases it's very small. Now, when you are, okay, now, right, this is your log operator, that is, so each one of these is your edges. Why do you think that, I mean, so suppose I asked you, right, what will be the, for a blob, right, if I asked you, where should it fire, right? If I asked you at what, so what should be that sigma, right, at which it should fire, then first of all, right, I mean, you know, right, prior to even arriving at the equation, which is very simple to actually derive, how would you analyze it? Think about it. Why is that so? Yeah, you're right. So why is that so?
So at some point, the minimum, since it's negative, that will come out to be maximum when both are matching.
Yeah, you are almost there, but I just
The sigma should be the width.
sigma.
Should be that width of
No, see, what he is saying is this zero crossing should match this. That's what he is saying, right? Oops, what happened?
and that zero crossing should match that.
With zero crossing should match what? This zero crossing? No, I have only one log at some scale. We are trying to see with respect to one of them, right? We are saying that we'll get a kind of maximum response. Correct. So a response is like what? I mean, when you take a sort of, you know, a dot product, right, between the two. So the point is this, right? When this guy comes and multiplies this, what will happen, right? Because of the fact that from here to here it's all 0. If you multiply that with this negative, this negative has no role, and all that you will end up is adding up these areas, right, under whatever is above 0, the positive one. If you had something which is very big, right, then basically what will happen is then all of so for example, so what will happen is, right, so this portion, so if you try to see, right, there is going to be a negative portion right here. See, from here to here, if you see, right, there is going to be a negative portion of this guy which will actually enter. Can you see that? I mean, similarly from here, right, you will have actually, so because of the fact that, hey, 1 minute, no, I think, right, this is the other way around, right? So you have 1 and then you have 0. Okay, no, I mean, right, negative will get knocked off because you have a 0, but then the positive area will shrink, right, because of the fact that you have 0 for that big, right, that big a width. Do you guys see this? The negative won't come because you're multiplying it with 0, no, that won't come. But what will happen is the positive area that you're considering will shrink because your zeros are extending beyond the lobe. In contrast, if I make it very small, right, then what will happen? You will actually get this kind of, say, negative portion into the area calculation.
So the overall response will be
Yeah, Which negative area? Not the one here, because that is going to 0, but this one, which is on the fringes, right? That will come in, no, because you have a smaller width, right? Therefore, those guys will come in. In between, the middle one won't come because multiplying that with 0. So, the best case is when just you get the positive areas that are all adding up, right? And okay, that's one way to actually, right? One way to kind of think about why it should snugly fit in. And when you say should snugly fit in for a log, it means that the blob width should actually the zero crossing should match that. Right? When that happens, you'll get the maximum response, right? And because our whole thing is about blob detection, right? So then, right, one can even argue that okay, right, I'm going to leave it as an exercise, right?